it working? Yes? Okay. So, I have to tell you the definition of semi-strict quasi-concavity. Let me recall briefly quasi-concavity and strict quasi-concavity to compare the three notions. It's the definition we have been working with all the time. Is the same but with strict inequality whenever ends. So for every xi with f x different from y, and for every lambda strictly between 0 and 1. And in fact, it's clear from the definition that now it's better. Okay, now it works. Thank you. It's clear that every strictly quasi-concave function is quasi-concave because equivalently, I mean, for x equal lambda, this is for x equal y, this is automatically satisfied, and for lambda equal 0 and for lambda equal 1 as well, this is automatically satisfied too. So here I could have written equivalently for every xy with x different from y, and for every lambda, oh sorry, this is lambda strictly between 0 and 1. And for every lambda strictly between 0 and 1 without altering the notion of quasi-convexity or quasi-concavity. So in this way we compare the two notions and we see that strict quasi-concavity implies quasi-concavity. But now it's the term of semi-strict quasi-concavity. And I think that after complicated time where people were using confusing terminology, this is the prevailing terminology, I think. So U is semi-strictly. Quasi-concave means U of x, 1 minus lambda x plus lambda y is greater than minimum ux uy, but not necessarily for every xy that are different. but for every xy at which u takes different values. Okay? So, of course, if it takes different values, they are different. Okay? This means that strictly quasi-concave functions are semi-strictly quasi-concave. So if you have a strictly quasi-concave functions, if you have 2 points in which the images are different, then they are different. So you can apply the definition of a strict quasi-concavity to deduce this strict inequality. So I'm saying that strict implies semi-strict, but not vice versa. We have this implication and this implication. But from here, you cannot move to quasi-concave. There are functions which are semi-strictly quasi-concave, but are not quasi-concave. Do you know an example? There is a classical example. Mod x, the sine of x. This is the sine of x. Let's see. This is not the example in mind. No, because it's undefined at 0. No? Which value you assign at 0? 0. Yes. Yes. In fact, yeah, you are absolutely right. In fact, there is a simpler example. I mean, the contradiction comes just on the right. The left does not play any role. So even though this function is very simple, it's unnecessarily complicated. And so the example I was going to tell you, which is somehow equivalent to this one, is at 0, 0, and everywhere else 1. Okay? Because if x is x, the origin, and this is y, u of x is 0, u of y is 1, so they are different. No. It was working on the left. Okay? So the example should be let's say 0 and minus 1. Okay? So this is the graph. If I am not wrong. So if x is 0 and y is this, then u of x is 0, u of y is 1, so they are different. But between x and y, I cannot say that the value is strictly greater than the value at the smallest value of y, because it's equal. So your example was correct, but I was analyzing it on the right. I should analyze it on the left. Okay? But then the right was not playing any role. So here I can also erase this. I can put here whatever you like, and nothing changes. So you have an example. Well. No, this is semi-strictly quasi-concave. Should be semi-strictly quasi-concave, but not quasi-concave. Yes? semi-strictly quasi-concave. Again. So I need on the relative interior of the interval, I need to have this inequality. It was correct because the minimum, it would be correct, I think, with this example. Okay? No? With example, because, no. With this example. Because when I consider any point, let's say, let's define u of x equal 0 if x is different from 0, and minus 1 if x is equal to 0. If I take, let's say, any y positive, no, and x will be 0, so u of lambda I between 0 and 1, sorry, I forgot to say here lambda between 0 and 1. And I multiply with lambda, then lambda I is also positive. Then u of lambda I, because lambda I is strictly positive, would be 0, which is strictly greater than minus 1, which is the minimum. Okay? So now this function here is minus 1, this is a semi-strictly quasi-concave. Okay? So now your example worked on the right, but not on the left. On the left, there was no mistake, but it was not necessary to consider that part. And however, this function is not quasi-concave, because if we consider any level between, this was minus 1, not 0, sorry. So this is the graph, all the horizontal axis, except at this point, which is that. If we consider a level between minus 1 and 0, we consider this level, what is the corresponding upper level set? Is all the real line except the origin, which is not a convex set. So not every upper level set is convex, then the function is not quasi-concave. But in the 1970s, Karamardian this is an Armenian name, but I think he was working in the US. Karamardian proved that if your function is quasi-concave, semi-strictly quasi-concave, and upper semi-continuous, it must be quasi-concave. Well, probably he was doing with quasi-convex. So, of course, we can change the sign here to give strict quasi-convexity and semi-strict quasi-convexity. This is not problem. You change the inequalities on the right and mean with max. Then what he proved is that a lower semi-continuous, semi-strictly quasi-convex function is quasi-convex. It's equivalent. Well, so here we only need semi-strict quasi-concavity, but of course a strict quasi-concavity would also work because it's a stronger condition. Then the proof is contradiction. Assume that for some x in x of p, this equality is not satisfied. Then this means we have a strict inequality here. Because the inequality is always satisfied because x is optimal under p, in particular it's feasible. Then, consider this assumption. This assumption is very mild, simply saying that under the given prices, there is something that you prefer to anything you can obtain under these prices, but you cannot afford, of course. Okay, this means that for some x, u of x is greater than v of p. So it is greater than u of y for every y satisfying the budget constraint. Normally this happens to us every day. Okay? So this is not an exceptional situation. Now, consider this x bar that we would like to buy, but we can't. So there exists x bar. I can take x bar in R plus n such that x bar, u of x bar, is strictly greater than v of p. Then it is too expensive. This means p of x bar, p times x bar, is greater than 1. With px bar less than or equal to 1, this inequality would be impossible. Because the value of u at this point would be less than or equal to the optimal value, which is v of p. Then we have p of x less than 1 and p of x bar greater than 1. Both are in R plus n. And then at some intermediate in the segment, joining x with x bar, there is some point in that segment for which the value at p is equal to 1. So there exists lambda between 0 and 1 such that p 1 minus lambda x bar plus lambda x is equal to 1. The existence of this lambda is not any mystery. You can solve the equation. So if you do it, then you get that this particular lambda, which is unique, is px bar minus 1 divided by p x bar minus x. Okay? This is the lambda that solves this equation, which is easy to see that it is between 0 and 1 strictly. Actually, it cannot be 0 and it cannot be 1 because then we obtain the points x bar and x which don't satisfy this equality. And we are almost done. Then v of p, what can you say of v of p? Using the fact that this point we have just constructed satisfy the budget constraint. That this is greater than or equal to u at this particular point. Okay? Because V of P is the largest value under this constraint. But now we are assuming that U is semi-strictly quasi-concave. And we have lambda strictly between 0 and 1. And U of x bar is greater than U of x because V of P is greater than or equal to U of x. Because x satisfies the budget constraint under P. X is in the demand set. Yes? Is it okay? You are asking about what? This, which one is not? X satisfies the budget constraint corresponding to P. It is in the demand set. Then the optimal value under P is greater than or equal to this particular value. And then U of x bar and U of x are different. So this is greater than or greater strictly greater because of semi-strict quasi-concavity than the minimum between the two, which is clearly U of x. No, as said there. But U of x is equal to V of P. Because x is optimal under P. So the value of the objective function of the consumer utility maximization problem is the optimal value of this problem that we call V of P. So we have reached a contradiction because this inequality is strict thanks to semi-strict quasi-concavity. Okay? So this proves our result. Another result about what can we say when the quasi-concavity assumption is refined. Is that, it's another proposition if you want. So what can we say when U is not only semi-strictly but also strictly? Then in this case, for every price vector, the cardinality of the demand set is at most 1. It may be empty, but it can have at most 1 element. If we have non-emptiness for some reason, then we have a demand function, because the cardinality is always 1. And the proof is extremely simple, could be left as an exercise, but so suppose x1, x2 are both in the demand set corresponding to x of p, then, and they are, okay, and they are different, then take the midpoint, then by strict quasi-concavity, this should be greater than the minimum. First of all, we have both are feasible. Px1 under P is less than or equal to 1, and Px2 is less than or equal to 1. Okay, both are feasible under P because they are optimal. But then the midpoint is also feasible because the feasible set is convex. So you have P 1/2 x1 plus x2 less than or equal to 1. That's quite clear. Then U of this midpoint is greater than the minimum by strict by strict quasi-concavity. But these two numbers are V of P, both of them, because they are optimal under P. So the value of the objective function at these points coincides with the optimal value, which is V of P. And then we get a contradiction because we have obtained a feasible commodity bundle for which the objective function takes a value larger than the largest, which is V of P, which is a contradiction. Okay? So, well, these are the just little results I wanted to mention in connection with generalizations of concavity. Now it's time to talk about monotonicity of demand. We have a demand correspondence, sometimes a demand function, and we want to know when such demand objects are monotone. A first very important warning. You have to change signs. What economists call monotone is what mathematicians would probably call dissipative. So it means that minus the mapping or the function is monotone. Okay? But first, I don't know how much familiar you are with ordinary monotonicity in mathematics. Should I recall? Okay. So I first say a few words about monotonicity in mathematics, and then we will have signs, and then we will talk about monotonicity in consumer theory. The point is that, so monotonicity, both in mathematics and economics, is for mappings from a space into itself. In mathematics, actually, one works with abstract topological vector spaces, and then the mapping don't go into itself, but into the dual space. Okay, only in Hilbert case, they go from the space into itself by the classical identification of a Hilbert space with its dual. But, and And then what, in the one variable case, monotonicity in mathematics is taken as a generalization of non-decreasingness, whereas in economics is taken as a generalization of non-increasingness. This is why we have to change signs. So let us get some inspiration in the definition of monotonicity, non-decreasingness for a real valued function of one variable. So suppose we have a function f from R into itself, or from a subset of R into itself. What does it mean that is monotone in the sense of non-decreasing? This means that whenever you have x less than or equal to y, then you have f of x less than or equal to f of y. How to extend this definition to the case when f does not go from R into R, but from Rn into itself? There are several ways, but which one is good in the context of convexity? So to make it convenient in the context of convexity, we have to rewrite this monotonicity condition in a different way. Instead of in the form of an implication, or instead of using quantifiers saying for every x and y with x less than or equal to y, we can write it in the form of a product. X minus y times f of x minus f of y is non-negative for every x and y. It's the same, because this is saying that the two factors, since the product is non-negative, have the same sign. So if x is less than or equal, if x is equal to y, it does imply nothing, but it does imply nothing here. Okay, well, it implies, in this case, if x is equal to y, we have f of x less than or equal to f of y, and f of y less than or equal to f of x, so they are equal. Here not, if x is equal to y, so let's try it. But x equal to y has no interest because they are the same and this is automatic. So let's write equivalently this condition with a strict inequality. Okay? Then if x is strictly less than y, this is negative and this is non-positive, so inequality holds. And if y is the larger, the same, or x is the larger. So this is equivalent to monotonicity. Then it turns out that in the Rn case, the suitable definition of monotonicity is the same, but with inner product. So now we are dealing with vectors. X, y, f of x, f of y are vectors. So the condition is x minus y inner product f of x minus f of y is greater than or equal to 0 for every x and y. When this property is satisfied for every pair, we say that the operator is monotone. More generally, we consider set-valued mappings. then the condition is the same, but now f of x and f of y are not just elements, but are sets. The condition is for every x in capital F of, for every x star in capital F of x and every y star in capital F of y. So the condition, one says that this is monotone if x minus 1, x star minus y star is greater than or equal to 0 for every x and y in the space, every x star in f of x and every y star and in f of y. Okay, which reduces to the previous definition in case if is a function, single value. Why are these conditions important? Because they are closely related to convexity. You know that for one variable functions, one variable differentiable functions, convexity of the function means non-negativity of its derivative. The same in several variables. So if f from an open subset of Rn, convex and open, is differentiable, then f is convex if its gradient is monotone in this sense. This is a monotone operator. Proof is very simple. I think I can prove both implications very easily. Should I try? No? So one follows immediately from the fact, implication from left to right is an easy consequence of the fact that the graph of the function is above the tangent lines, the tangent hyperplanes. And the opposite implication also holds by using the same trick, but with a point in the segment. Okay? Doesn't take more than 5 minutes. Good. So this justifies, does this definition of monotonicity is the appropriate one in this context, in the context of convexity. Because convexity of the function is equivalent to monotonicity of its gradient in the differentiable case. But what about not necessarily convex functions? Suppose I have an arbitrary function extended real valued, not necessarily convex, but in spite of possibly being non-convex, I consider it subdifferential. The problem is that the subdifferential would be empty at many points, possibly, to many points. No? But I still can consider the subdifferential as we observed, and this is an easy exercise that the subdifferential, so-called Fenchel subdifferential, is still monotone. This follows if you agreed that this implication is easy to prove, then you must agree that monotonicity of the subdifferential is always monotone, even if the function is not convex. Then how can we distinguish convex from non-convex? Consider this function with this graph. This is -1, this is 1, this is 1, and the slopes are -1, 1, -1, 1. Can you tell me the subdifferential operator, the graph of the subdifferential operator of this function? So let us see what happens between -infinity and -1, between -1 and 1, and from 1 to +infinity. So, if the point is strictly less than -1, then this is the only straight line through the point in the graph which is below the graph of the function. This means that here the function is the constant function -1. Then what happens at -1? What is the subdifferential of this function at -1? Then you may give a wrong answer, I warn you. What is, you may give, but not necessarily. So what is the subdifferential of this function at -1? -1, 1. This was? Yeah. This was exactly the wrong answer I was expecting. Thank you. So if you tell me that every number between -1 and 1 is a subgradient here, then you are telling me that any line through this point with a slope between -1 and 1 is below the graph of this function. So you are telling me that this line with a slope 1/2 is totally below the graph of this function. Do you insist? I told you that the notion of subdifferential for non-convex functions is non-local. So you need to know the information, have to use the information everywhere. And you were just looking at here. You were myopic. Okay? Then no. So, okay, a second chance. What is the subdifferential there? -1 to 0. I mean, you can still have zero slope, horizontal slope, and be below the graph. So exactly. So this is the graph of the subdifferential. Now take any point strictly between -1 and 1. What's the subdifferential there? I mean, take any point here, and please give me the list of all the lines through this point which are below the graph of this function. There is no, this is what you are saying. Exactly. It's the empty set. Okay. At these points, there are no subgradient. In fact, it's very easy to prove. When I say very easy, probably I will not repeat this term very often, because when I say very easy, I am committing myself to make the proof in case you require it. So when I say very easy, is that I could get the proof now. So if you have a point where the subdifferential is non-empty, at that point, the function coincides with its convex envelope, with the largest lower semi-continuous convex hull that coincides with it. So in this case, this convex envelope is this function in which this part is replaced by the horizontal segment. So if at this point there is no coincidence between the function and its convex envelope, subdifferential. Okay? Okay, now you will not make the same mistake for the second time. You're not like me, who repeated the same mistake twice. I was behaving devilish. So what is the subdifferential at 1? Hmm? 0 to 1. Okay? So and then from this point on is the constant 1. In the same way as here it was the constant minus 1. So you see it's still monotone. Monotone means that for a one variable function, as you proceed from left to right, you go never down. You stay at the same level or go up. Okay? So it's monotone, in spite of the function being non-convex. Then what distinguishes, in the one variable case, convex from non-convex? I already gave you some clue, because I say when the subdifferential is non-empty, then you have equality with the convex envelope. Well, you can use this idea to, but no, this idea is not enough. I mean, but based on this idea, you can see the difference. The difference is that subdifferentials of convex functions of one variable are not only monotone, but maximally monotone. Maximally monotone means that the graph is maximal with respect to inclusion in the class of monotone operators. Okay, so maximally monotone. In the past, people used to say maximal monotone, then somebody decided that instead of maximal monotone, one should say maximally monotone. For me, both are correct, because maximal monotone is just an composed noun itself. But if you take it as an adverb, then it must be maximally. Use the terminology you like, but the terminology that has prevailed is maximally monotone. So here you can add many points. No, not this one. You can add this point, and then you still have the graph of a monotone operator. In fact, you can add all this segment, and this should be still monotone. In fact, when you are adding this segment, what you are getting is the subdifferential operator of the convex envelope of this function. In the one variable case, everything works pretty simple. Every maximally monotone operator one variable, is the subdifferential of some convex function. And this is if and only if. In fact, maximality is true in general. This was originally proved by Rockefeller, I think in the 70s, maybe earlier, maybe in the 60s. Okay? Subdifferentials are maximally monotone. He gave 2 proofs because the first was wrong and was published. And there have been other simpler proofs later on. Okay? Does the convex hold true? In the one variable case, yes. But in the several variable case, no. There are maximally monotone operators which are not subdifferential operators. And they are useful in applications. Then what do you need on top of maximal monotonicity to make sure that your operator is the subdifferential of a convex functions? You need a property called cyclic monotonicity, which is automatically satisfied in the one variable case, but not in higher dimensions. I'm not going to insist now about this cyclic monotonicity because we are going to find it somehow later in the demand context. We are going to discuss about cyclic quasi-monotonicity. Okay? And then I will tell you the relations between that notion and cyclic monotonicity. Well, I erased a result on which I wanted to make some comment. No, it's not erased, it's here. For differentiable functions, this is a characterization of convexity in terms of monotonicity. Is this nice? Yes. Is this useful? Yes. But in the one variable case is fantastic because non-decreasing functions are very familiar to us. We have a clear picture of their behavior. But with several variables, do you have a clear picture on the notion of monotonicity? I don't, and I have been working a lot on monotone operators. I understand convexity rather well. I can make a picture, etc., many pictures on convex sets, convex functions, etc. But on monotone operators, first of all, here it's very easy because the graph is in R2. But if the operator is defined on R2, its graph is on R4. Please don't ask me to make pictures on R4. I will refuse. Okay? So it's nice, it's useful, but somehow surprising. Why are you characterizing convexity in terms of something which is more complicated by convexity? Then the question is, can we do in the opposite direction? Can I characterize monotone operators in terms of convexity? Do you know the solution? The answer is yes. Do you know how? By the so-called convex representations, by using, for instance, Fitzpatrick functions. There is a way to represent maximal monotone operators by convex functions. And using these ideas, you can characterize monotonicity in terms of complexity. So you have an operator, arbitrary operator. If you have a convex representation, if and only if it has a convex representation, is monotone. Well, no. If it has a convex representation, it is monotone. And if it is maximally monotone, even you can relax this assumption, it has a convex representation. If you don't need a representation but something weaker, then you have an if and only if. An operator is monotone if there is a convex function satisfying some properties. So this is a characterization of monotonicity in terms of convexity. Something difficult in terms of something easier. The initiator of this theory was Simon Fitzpatrick, an Australian mathematician who passed away long ago. I never met him. But interestingly, I was unaware of his function. But somehow when working with Michel Terra, we rediscovered it. Fitzpatrick introduced what nowadays is called his function in 1988. But he published this in a proceedings volume of some Australian workshop. So nobody knew it. Well, he knew, and there was another person who knew. And then, working with Michel Terra, we found out this definition, and I told to Michel, look at this. And he said, no, but this must be equivalent, and he was partially right, to something which is already known, which is the representation of monotone operators by saddle function. I say, yeah, but it cannot be the same because our function is uniquely defined, and that one is not. So I'm sure there are relations, but then he was not very interesting, but after some years, I convinced him that we should publish. So we published a short note introducing this function and giving some results on it. And before the paper was published, he sent the preprint to Borwein, John Borwein, and Borwein said this function already existed. This was introduced by Fitzpatrick. But luckily the results we had obtained were different, so our paper was saved. And then we added in proofs. This function was introduced by Fitzpatrick. The interesting thing is that after we rediscovered the Fitzpatrick function, everybody, including Borwein, who knew it, everybody started to work on Fitzpatrick functions. And what is the idea? To obtain results on monotonicity using convexity. It was already observed that the assumptions you need in theorems on monotonicity and for theorems on convexity are the same. Now you know why. Because you can give convex analytic proofs on results on monotonicity. So in this way you can prove known results but also new results by using these techniques. It's a very beautiful theory which I really love. Okay, but now it's enough. Then this was just a comment that here you have convexity defined in terms of monotonicity, and then but you can do it otherwise. The result, it's very easy. The result. So, and as I said, when I say very easy, it means that if you say I want to see a proof, I can provide it with it. Okay. But now, it's time to go back to economics. to demand correspondences. And we say that so we are considering a consumer utility maximization problem, and X is the corresponding demand mapping, set valued mapping. We will say that X is monotone. If the following implications holds true. For every P in R plus N, every P and Q in R plus N, if X is in X of P and Y is in X of Q, the product P minus Q X minus Y is less than or equal to 0. So is monotonicity with a minus sign. Monotonicity, as I referred to it so far, was greater than or equal to 0 here. So, but I'm going to use, because we are dealing with a topic in mathematical economics, so I'm going to use the economist's terminology. I'm going to call it monotone, although according to what we have seen earlier, I should say that minus X is monotone, okay? So be very careful about these results. And this has to do with the law of demand. In fact, it is called the law of demand by economists. So the law of demand simply means X is monotone. But this is a law which is not always fulfilled. So we will see probably this after lunch. What ordinary people understand by the law of demand is that if the price of one good increases while the other prices remain the same, then the demand for that good decreases. That's what you said, it should be like this. Look, that this is telling this, but it's telling more. Because suppose today you go to the market and plus prices are Q. So in view of these prices, your demand is Y. But tomorrow you discover that good I is now lambda rupees more expensive than it was yesterday. So this means that the price today is the price that it was yesterday times the unit vector EI. And lambda is positive. The price has increased. Now you say, okay, in view of that, I buy X. Then, if the demand is monotone, you have this inequality, which in this case, sorry, P is not, not everything is for free except lambda. The prices are the ones they were yesterday, Q, but the ith good has increased its price by lambda. Okay? Then if you replace all this here, then P minus Q is lambda times EI. In our product, S minus I means lambda xi minus yi is less than or equal to 0. If you divide by lambda, then you get that xi is less than or equal to y, which agrees with your intuition. So the price of good I increase, and I cannot buy more now than I bought yesterday, okay? X is your demand today. Y was your demand yesterday. So this happens when the demand is monotone. Because you were saying that this should always be the case, mathematically, what you were saying is that a demand corresponding should always be monotone. And I will give you easy examples, mathematical examples, economic examples, proving that this is not necessarily the case. Extremely simple examples. But before, we are going to see that even if the law of demand does not always hold, monotonicity does not always hold, then a weaker notion called quasi-monotonicity is very often satisfied. What do we call, what is quasi-monotonicity? There are several ways of stating quasi-monotonicity. Again, be careful, we are changing signs. Okay, but in this context, this condition can be rewritten by saying that P, x minus I plus Q, y minus x is less than or equal to 0. This is the same. So we are writing that the sum of two numbers is non-negative. This implies that at least one of the two numbers is non-positive. The smallest is non-positive. So every monotone, in that sense, operator satisfies this weaker condition. It's very easy to give examples to prove that the converse does not hold. And if we have an operator satisfying this condition, then X is said to be quasi-monotone. Monotone. So X is quasi-monotone if for every pairs Px, Qy in the graph of X, we have this inequality. Of course, in the mathematics context, instead of mean here you have max, and instead of less than or equal to, you have greater than or equal to. One has to change signs. I warn you because quasi-monotone operators are very popular. They are somehow related to quasi-convex functions as monotone operators are related to convex functions. Well, we are going to see that under a mild assumption, even though a demand function need not be monotone, but it's quasi-monotone. Even more than quasi-monotone is so-called cyclically quasi-monotone. So why we say that X is cyclically quasi-monotone? If whenever we have a finite number of vectors in R plus n, regarded as price vectors, and corresponding elements in the demand sets we have that the minimum of pi xi minus xi plus 1 I from 1 to k is less than or equal to 0, admitting that x plus 1, that we define x plus 1 is undefined. We only have x1, xk. But here I may be k. So I am considering xk plus 1. I have to define x plus 1. So we go back to the beginning. This is why the word cyclic. So xk plus 1 is by definition x1. Okay? This is this condition. For every k, for every number of vectors, for k equal to, this is quasi-monotonicity. No? For x equal to, we are saying P1, x1 minus x2, plus P2, x2 minus x3, that x3 is x1, is less than or equal to 0. So cyclic quasi-monotonicity is much stronger than quasi-monotonicity. Quasi-monotonicity is just the case k equal to here. This is, of course, related to the definition of cyclic monotonicity for operators, which I already mentioned. Again, going to mathematics, you have to replace min with max and less than or equal to with greater than or equal to. And looking in this way, this is weaker than the condition sum of pi xi minus xi plus 1 greater than or equal to 0. And it's very easy to prove that subdifferential operators satisfy this property, because the idea is, suppose pi is in the subdifferential of xi. So you have x2 greater than or equal to f of x1 plus p1 x2 minus x1. x3 greater than or equal to fx2 plus p2 x3 minus x1, x2, etc. until you get xk plus 1, which is x1, greater than or equal to f of x k minus 1 plus pk minus 1 x1 minus xk plus 1 minus 1. Then if you add all this and you add all this sum coincides with this sum, and you obtain that this sum is less than or equal to 0, which is exactly what we are saying here. So proving that a subdifferential operator is cyclically monotone is quite easy. And then maximal monotonicity together with cyclic quasi-monotonicity means you have a subdifferential operator. Okay? Well, then we are going to see now or later. I don't know at what time we started. Yeah? We already spent 1 hour. So what we are going to see after lunch is that when the utility function has no local maximum, the corresponding demand mapping is cyclically quasi-monotone. For every set of points in every finite set of points in R plus n, every set of k points, and k is arbitrary. You take elements in the corresponding demand set, then you make this computation, and it's less than or equal to 0. It's not just but for one particular. In the same way, is quasi-monotonicity is for every PQ, and then XY in the corresponding sets. This is for every P1, PK. And X1, XK in the corresponding sets. Okay. This is related with what economists call the weak axiom, I think, of reveal. Probably it's not exactly the same, but it's related to it. Okay, so you said it's time to stop? Okay, thank you.